Okay, so this is a kind of a schematic. Uh, we have a spring, let's say, or some medium, could be water, but water is dispersing, it's complicated. So you don't even know what that means yet. But let's assume it's a spring under some tension. You have simple harmonic motion at this end, we're driving it, maybe I'm just moving my hand, okay? Cosine or cosine of pi t. How long does it take me to go through a cycle? Don't say it, just hold up fingers or whatever. What's the duration of a cycle with it? Am I moving my hand faster or slower than I have to? Is something over pi? Two? Yeah. I think it's two. If it t's in seconds, it's 2 seconds. Because to go take this cosine through a complete cycle, pi t has to go through a cycle of 2 pi. So one person was indicating a division by pi, yeah, but put the 2 pi on top. So you had that right, and then you got to the right thing, okay? I mean, that's how you look at this. If this changes by 2 pi, you've completed a cycle. So set this equal to 2 pi, solve for t, and you know how long the cycle took. If you know how long the cycle took, well, you can figure out what has to go in front of t here, okay? Now, when I said familiarize yourself with the introductory problem sets, I said that a week ago, okay? It doesn't look like you've done it. So all I'm saying is I understand time and I understand constraints. But it's going to take us a lot longer to get through this if you're not familiar with introductory problem sets. And we don't have longer to get through it, so that means we're going to go through it, but not as deeply as we would like, which means it's going to be harder for you to prepare for the test, which is going to be what it is, okay? Not going to be a hard test because we're doing kind of a quick survey of a lot of topics, but you really need to start with those introductory problem sets and not just read them, work them. Make sure you understand the symbolic solutions, make sure you understand the relationships as best you can. I will say there's one problem there. It has an absolutely absurd answer. Okay, I was looking through. I reviewed them. It's been a long time since I wrote them. But every time I review them, I kind of like them. And I kind of think they get the job done, and they did get the job done back when I was using them. But it was for lower level physics. It was just a superficial introduction for this physics, but it's not all that superficial because it gets to the heart of the concepts that you need to put together to understand this stuff. Okay. And you know what we're doing here is I'm going to pose some problems. You need to solve the problems. By working through the problems, you'll spend less time than you probably would on the Pearson materials, but you'll learn to solve problems rather than just do whatever Pearson runs you through, okay? Because y'all are smart enough to do that. Okay, but make sure that you're preparing. Okay, if you haven't, you know, glanced at the textbook, if you haven't looked at the introductory problem sets, you're not prepared. Because this is one of the fundamental questions. Okay, so anyhow, okay, so wave propagates at 5 meters per second, 3 meters down the way. What's the equation? Everything that happens here happens at some, at any point on the graph, whatever happened at any point on this string, what happens here is going to happen later. That's the key concept. Okay. So what happens? Happens 3/5 of a second later at x equals 3 meters. So the proposed solution is 4 times the cosine of pi t times t minus 3/5 of a second. Okay. No, that does that fit common sense? Or if it's later, should it be t plus 3/5 of a second? No, I think you're right. Okay, so here we have it. Okay. Now we can test this out. That would be at time t. Right down your conjecture for that one. Give you just a minute or less. Give you a chance to figure it out. Takes time. Get there, so y equals 4 times the cosine of pi times the quantity t minus x over c. Shut up and put a little crap in this. That's. Okay, so we've got this, which we can of course write as 4 times the cosine of pi t minus pi x over c. Which is 4 times the cosine of omega t minus kx. K is pi over c, but in general it's omega over c. Okay. Now. Omega is 2 pi times frequency. You've been through even the first few of the introductory problem set. You understand what that means. And you should understand that in terms of the unit circle and everything else. Omega is your number of radians per second. This is your number of cycles per second, right? And I think I wrote that down wrong, so I don't understand it. Okay. Wrote it down backwards. Which is why you always want to explain it to yourself after you write it down. Okay. F is 2 pi omega, because omega is your number of radians per second, and F is your number of cycles per second. You've got 2 pi radians in every cycle. And I wrote it down wrong the second time because I'm thinking. Okay. Now let's see if we can reason this out again. I wrote it down right the first time. I don't know what made me think it was wrong. But you know, okay, here's your circle. You know, you do one cycle around the circle. That's 2 pi radians. And of course, it's the unit circle that drives the cosine, right? I mean, there's no unit circle out here, but that's the way you think of the cosine. So as I said, omega equals 2 pi F. It's hard to say why that was. I don't know, something didn't click right. Anyhow, there it is. So omega is 2 pi times frequency. That's just the relationship between how far it is around the circle, how many radians around the circle. Okay. Every cycle is 2 pi radians. Okay. So omega is 2 pi F. So K equals 2 pi F over C. But F lambda equals C, and you should totally know the meaning of this, having pondered the first 8 of the, about a third of the introductory problem set. What's this mean? This means cycles per second, and lambda is a wavelength, which is the meters per cycle, for example. If you multiply the cycles per second by how far you go on each cycle, you find out how far you go each second. And I'm not going to repeat that. That's right there, written in the introductory problem sets in a way I think is understandable. Okay? I refined those people to understand them. Okay? And found they didn't, made refinements. Except for that one bizarre result. I still know where that came from. Okay. So that lambda is C over F, and F over C is reciprocal of lambda. K equals 2 pi over lambda. That's the wavelength. Omega T is radians per second times T, it's in radians. kx is 2 pi over lambda. In SI units, I'll go ahead and use SI units, it's radians per meter times x, which comes out in radians. Use some other system of units and just work out what the relationships are, okay? So you have radians of oscillation, and you have radians of position. Now, to make sense of this, fix t don't like the notation here, but I'm gonna call omega t phi sub t, and we understand that that's fixed. Okay, it's a constant number. Constant number of radians, because omega t will be in radians. Of course, that's 4 cosine of kx minus phi t, because cosine's an even function, right? So to get from here to here, it just comes up because the cosine's an even function. Well, we can graph that. We graph y versus x. Y equals 4 up there. Y equals 4 down here. Phi t is just a constant. So whatever phi t happens to be, this point is 0, 4 cosine of phi t. And now we can sketch the graph. It's a cosine function. It starts here. Here's the top, here's the bottom. Okay. We have a little bit of an ambiguity. We don't know whether to start up or down. Okay, well, that's going to depend whether phi t is from 0, 180 degrees, or 180 degrees. And, sorry, between negative pi over 2 and pi over 2, or negative 90 and plus 90, or between 90 and 270. Okay, not going to address that right now. I'm just going to say, okay, well, it could be this way. We don't know what phi t is. Okay, well, the distance from here to here is a wavelength, isn't it? Because if x changes by lambda, kx changes by, okay, it's 2 pi over lambda, right? K is 2 pi over lambda. The reason we call this a wave number, well, it's 2 pi over lambda. So if x changes by lambda, kx changes by 2 pi. So write that down. Interesting when you want to digest. And keep. Okay. Because you don't understand the dynamics of the sine or cosine function. Unless you understand that, you might be able to put it into a calculator and get the right answer, but do you understand it well enough to understand how all this stuff hangs together? And, oh gee, okay, I kind of messed up there. When I labeled this distance lambda, it's not really starting at 0 here. I went all the way back to the axis, but it's from here to here, right? There's a complete cycle of the cosine function. One cycle. Which occurs when x changes. Since k equals 2 pi over lambda, kx will change by 2. And I mean, I know where I was looking to draw this line. Here, here. I think I pointed from here to here. Notice where to put that line. Okay. So again, what happens here is I'll emphasize that. And that's the comma there. I'll just leave the comma out. Maybe. You can have this board run over. But there it is. Now, what happens as t increases? As t increases, phi t increases. Okay. So we can draw this again. Okay, here is t equals 0. Phi t, which is omega t, equals 0. So this is just the graph of for cosine of kx. Be 0. And remember that negative kx cosine of negative kx is the same as cosine of kx. But it's gonna get us in a little bit of trouble. Because the signs are wrong here, we're gonna see why. Okay, now we're gonna let t equal whatever number runs this thing through a quarter of a cycle. Okay. So what would t have to change by for omega t to change by a quarter cycle? Quarter cycle is how much change on the unit circle. Quarter cycle, the position of the unit circle goes from 0 to pi over 2, right? Okay. So that omega t should equal pi over 2. So the t should equal pi over 2 omega. Remember, omega is in radians per second, or radians being kind of a phantom unit, it's a reciprocal second. So this will be in seconds, right? Or if you prefer, this is in radians per second, the pi is in radians, the radians divide out, seconds flips up into the numerator. So t is pi over 2 omega. In this case, we have y equals 4 times the cosine of kx minus pi over 2. Now, pi over 2 corresponds to this increment here. Okay. In other words, if the argument changes by pi over 2, that shifts the graph let me write it out here. Talked about it last time, but in a slightly different context. It's right, pi over 2k, which is pi over 2 times 2 pi over lambda, which is going to be 1/4 wavelength. So these lines mark quarter wavelengths. From here to here, peak to peak is a wavelength. I divided the wavelength into 4. Here, here, here. Make sense? Okay. So the graph is going to shift right. That means this point is going to shift over to here. This point is going to shift over here. This point is going to, this point will shift over here, and so forth. So our graph will look like this. And of course, we still go back to the origin, right? Make sense? Pretty straightforward. Okay. So this thing is shifting to the right. If we go to t equals pi over omega, you fill in the details, it's gonna shift right again. Now, these are snapshots of a wave at time intervals, pi over two omega. Okay? So this is t equals 0. This is one time increment later, the graph is here. One time increment later, it's over here. The graph is shifting. The graph is shifting to the right. At what speed? Well, graph shifts right. Why? Lambda over 4. Quarter of the wave. And from that, you can figure out the frequency and all that kind of stuff. Okay. So again, ideally, you would have come in pretty much knowing this time shift thing. Okay. And then this development would make a lot more sense to you while you're looking at it. But it give you some problems, dude. I hope you've been doing the problem. I think. Send it out. You know, the one on thermodynamics and the efficiency of that heat engine, which bottom line is the one thing you need to figure out to understand most of the other stuff I want you to know. Okay. And if you know PV equals nRT and a couple other things that we've gone over, you can do it. But you're going to have to engage with the problem. And if you have difficulty with the problem after engaging with it, let me know. Okay. If you figure out that problem, and everybody I think has got the, you know, shown in class, and you've got what you need to be able to figure it out, you'll be able to do it. And you'll learn a whole lot more in the process. You learn in a similar amount of time with Pearson. You learn something about problem solving and put together a lot of interesting physics. Okay. In general, as I developed in class last time, hopefully you watched the video. Y is a function of T and X A cosine of omega T minus KX. Everything we've done here tells you what all this means. So you gotta know what K means, you gotta know what omega means. But you can also think so. What would you get if you multiplied omega by K? What units would you get? Well, you get radians squared per second meter, wouldn't you? That make any sense? Wouldn't make any sense to multiply these. It wouldn't have any meaning. What if you divide omega by K? And that's in, well, it's very clearly in. Hopefully you thought it one before I said it, it's in meters per second, right? has the definition of omega, okay, not just because the definition of units. C equals omega over K. Which equals, of course, omega over 2 pi over lambda, which is omega lambda over 2 pi, but then omega is 2 pi f. So C equals F lambda, which is just common sense introductory problem sets beat into you immediately in a way that you understand. F is how many cycles per second, lambda is how far you go in each cycle, you multiply them, it's how far you go each second. Okay? But it kind of has to be second nature. When you see that, it's not just a symbol, not just something you use to get an answer. It's kind of meaning. And, you know, as I kind of said in pre-calculus, pre-calculus, in multivariable calculus, yes, really. You know, the whole idea of a projection, which I spent a good 30 minutes explaining the meaning of and so forth, comes down to a picture. If you've got that picture, then you see how to find the distance from a given point to the intersection of two given planes, or the radius of a sphere tangent to a given plane centered at a given point. You get a picture in your head by understanding the projection. Now, that can be important in physics too, and we're not actually that far from it when we get into some of the electromagnetism, but still, that's not my point. My point is, it's one of those foundational things that you have to understand at gut level, just like this is. As soon as you understand this, the rest of this and the idea of a time lag from here to there, everything else follows from those two premises. Okay, and if you understand it at that level, then there's a whole lot of stuff you can solve that you wouldn't be able to solve if you just memorize equations. Okay. Not that being able to use equations isn't important and valid. Sometimes you got to solve the equations and then think about what they mean. Goes both ways. Okay. That's your mathematical description of a traveling wave. Now, let's say we've got a wave happily traveling along. Moving in this direction. And we've got another wave happily traveling along. Same wavelength, same amplitude, but it's traveling in this direction. Okay? What's going to happen? Okay. Okay, so this is a wave. I'm going to say this is a reflected wave. So this wave we think of as just going on, okay? So it's not like they haven't met. It's that this wave has traveled down a string and hit a wall. And the wall reflects it. Demonstrate that in lab. Okay. There's stuff we would have done Monday, but A couple people missed, we had to do something else. Be sure you review that video. So there's a wave, there's a reflected wave. Okay, well, the wave will continue going. Okay, so let's just let the wave continue. And let's let the reflected wave continue. What have we got? We've got two disturbances at every point. It turns out they add up. It's called superposition. Okay? Superposition of the two states. You probably, if you read anything about quantum computing, I wish there's a lot of hope, but still, some skepticism of whether we can ever maintain the necessary states long enough to get reliable results. Instead of having binary states at every node or every, instead of having every unit having either a value of 1 or 0, you've got these quantum creatures, which can be in any of the number, could be an atom, usually is in some state, and it has essentially an infinite number of states, but it has a bunch of states that you can use. Well, traditional computers go by powers of 2. Quantum computers go by powers of however many states there are. And generally they have a superposition of states, so you can put all kinds of different states into one, what we call cube. Okay, now that's one aspect of superposition. That's not worked out how all that works together and how you program one. I never will, because it's pretty hard. A lot of people, a lot smarter and younger than I am, are trying to figure it out. Okay, and by the time they figure it out, I'll be, I don't know, incapable of understanding it most likely. Probably already am. Probably always was. But okay, there we have it. Okay, so we have a superposition here. Okay, which means that, well, you've got an equilibrium state. Let's say this is a string. So here's the equilibrium position or the configuration of the string. So at every point, let's just say at this point on the string, I'll draw a vertical line through it, point just a little bit to the left of that. There's a point where this one is as far above equilibrium as this one is below equilibrium. Okay? Which means that the net of those two is going to be 0 there. And it's going to happen like here. It's going to happen like here. It's going to happen, maybe about here. It's going to happen about here somewhere. It's going to happen, did I do something wrong? No, I didn't. Well, I probably did, but it wasn't what I thought. Okay, you're going to have one here, but maybe one about here. These would be regularly spaced. They don't look regular because I didn't draw the thing perfectly. Okay. You understand how at each of these red dots, one is as far above the equilibrium as the other is below. So when you add their y components, you get 0. That makes sense? It's not hard to see. So, I could draw these vertical dotted lines, but you get the idea. There are a bunch of points where that happens. Now, at some point, these two are going to give you a maximum. So, maybe about here, when we add the two where they're equal, maybe And maybe that's not the point, but it's gonna be twice as high as either of them. Okay, that's gonna happen maybe about here, maybe about here, maybe about here. Maybe not exactly there, but somewhere around there. Again, it's not perfectly drawn. And same thing on the other side. There should be one in here. And there'll be one over here. Shouldn't have drawn that one, shouldn't have drawn that one. So, you know, what you end up with is a wave that looks like this. At every peak, in every valley, or between every peak and every valley, and this valley here, and I put one there, what shouldn't have. You go through the red dot with Uri. Okay. It makes sense that you probably would get something that looked similar to this if you just added the amplitude or the Y values of both graphs. Okay, something I always want to do in pre-calculus, but I never can because too few people ever understand it. Is talk about you got two graphs, you add the two functions, construct the graph. That's hard for people to get through their head for some reason. Maybe just because I'm the one that's explaining it, but and somebody else might give a better explanation that actually clicks. But also just because I think it's kind of hard. Okay, kind of hard for me when I first thought about it. Nobody ever told me to, but I started thinking about it. Took a while to get comfortable with the idea. So I can't teach that pre-calculus, but we should be able to understand it. Okay. Okay, so. All right, well, this is fine. We need to line things up a little bit. And I think about one of the most decent valleys. Okay, now I'm going to move the point graph to the right. About a quarter of a way. Actually, you understand, if I move the white graph a little bit this way and the green graph the same distance this way, the peaks will match. And at that point, we'll get the highest peaks, but the peaks will always be on this line. Okay. Now, if I move them a little further, I can get a state where the peaks meet the valleys. Okay. So we could have a little more motion. Okay, so if this peak moved over to here, and the valley here moved over to here, because there's a valley here, right? So if this graph moves this far, and this graph moves this far, then this peak will meet this valley. Okay. These aren't drawn perfect because it's a little hard to see. When that happens, then at this red dot, we'll have peak meeting valley, okay? So we have peak meeting valley here. So I'm gonna draw the green graph. So that its peak is over here where this 0 point was, okay? So I'm gonna draw it like this. It's gonna have to go down here. Up the valley here, even up here. Down here. Something like this. The white graph. I'll draw some of the valleys here. And what happens? Some of the graphs is a flat line. Okay. Now, if they shift a little bit more, another quarter of a wavelength in each direction. These are what? From here to here is a wavelength. These are half wavelengths. If we move a quarter wavelength in each direction, what's going to happen? Well, in another quarter wavelength, this will be here. And this will be here. Okay, so in another quarter of a wavelength, the white graph is going to look like this. Gotta be careful because it's real easy to see how to. Not drawing it very accurately, very carefully. And of course, you're gonna have this emergent from the left. Okay, so that's what happens. And you see that that's what happens if the white graph moves a quarter of a wavelength, half this distance to the right. This peak will go to here. This peak will go to here. Uh-oh. Speak something up. Yeah, I did. Afraid I was gonna do that. Valley, peak has to be here. Valley here, peak here, valley here, peak here. Okay, so now each peak of the white graph is moved over this far. This peak moves over to here. This peak moves over to here. This valley moves over to here. And this valley moves over here to join up with this one. If we move the green graph, that quarter wavelength to the left, graphs map up. And again, we end up with the extreme version of this, okay? So what happens is if we look between, what are our colors? Can we have a color there? Seem to have one. I'm just gonna make a big thick white line. Okay, so I'm gonna now draw a white line through here. One of the points for the graphs for the orange graph comes out 0. Okay. Another point where the orange graph comes out 0. I'm going to say, okay, here are two walls. Here's the equilibrium position of the spring. using a different vertical scale, because I don't have room to make it as big as I made that one. We start out with this configuration, where it's down, then up, then down, then up, and so forth. And let's be careful. These lines should be equally spaced, and they really aren't. If this is half of them, half wavelength, this is a quarter wavelength, there's a half, and so forth. Okay, so if I start with this configuration, this configuration up here, I'm going to go down here. And then up here, down here, and then I'm up. Then I'm down on the next one. And the wave looks like this. Now, what this represents is a wave traveling to the right, a reflected wave coming from the left. Okay? And these waves are reinforcing between here and here. Okay. This is at one time. At the next time, it goes to this configuration. At the next time, it goes to this one. So the wave is first up at this point, then it's flat at this point, then it's down. So at this point of the graph is going, let's say from here to here to here, and that's going to keep going between here and here. Every quarter cycle, it's going to jump from here to here, or from here to here, from here to here, from here to here. Does that make sense? Okay, well, let's see what that looks like. And it's one thing to point to the board, it's another thing to get our hands on something. I'm not set up where I can do it on the screen, but we just took a chain and wiggled it faster and faster, fixed at one end. And what happened was just a little bit of wiggle, just a little bit of motion in my thumb, just a few millimeters. Sent a disturbance down the wave, got some energy into the wave, and most of the energy reflected back at us. If I wiggled my thumb at just the right frequency, then the wavelengths matched up with the distance from my hand to the wall. It wasn't really a wall, it was a handle of a drawer back there, but it worked. Okay. And it looks like I have 1, 2, 3, 4, then a half and a half, 5 half wavelengths. Okay, is that right? 5 half wavelengths is 2.5 wavelengths, right? I had one wavelength here, another one here, and well, okay, between here and here, between here and here, and then here's a half. Okay, so 1, 2 and a half wavelengths, 5 halves, 5 half wavelengths. That would cause one, two, three, 4 nodes. A node being a point, or if you looked at that thing, okay, there was always a series of points that really weren't moving much, right? They're moving a little bit because nothing is perfect. But points where there's little or no motion in the chain. Okay. So depending on the tension of the chain, if I get the frequency right, just right, I produce a wavelength that resonates within this distance. Okay? Now we're gonna do that in lab. We have them off. With the chain and with rubber bands. Rubber bands actually work better than that chain. Because they're lighter. And you can manipulate them easier. So that's kind of where we're headed. You could think about what the mathematical description of this would be. We'd have an A cosine of omega t minus kx coming in the opposite direction, A cosine of omega t plus kx. Put that together. And you can do a mathematical analysis. We're not going to do a whole lot of that, but you should understand that we can do it if we're going deeper into waves. And if you go deeper into waves in your future, you're going to get to do it. Okay. Okay, well, I gotta say, you really need to get into these introductory problem sets. You could have gotten a lot more done today. Okay. And it's not so much a matter of getting done, it's a matter of you're gonna learn more if you know something when you come in. Okay. You can always dig it out of the book. You can always dig it out of the introductory problem sets. Gonna have to extend it a little bit. One way or another, I'm gonna have some problems for you to do through next week. Okay, we're gonna spend the rest of this week on waves and optics. And we're gonna do that in lab, and we're gonna do it as best we can here. But we're gonna do it much better if you read the chapters on waves and optics and at least scan them. And then pick out the points where you pretty much understand and kind of try to nail it. And solve the problems that I've created for you, okay? That's what you really need to do. Then we're gonna have a test of everything we've done up to this point. And then we get into electricity and magnetism. And we're going through this other stuff kind of fast because we want to spend a good bit of time on electricity and magnetism because it needs time. Okay. It's a really important topic. Okay. Okay, you guys can go on, but this will be in the video. So that asked about the fact that when I did this, I had a cosine of kx, omega t minus kx plus phi. That's just a phase angle. The only effect that has is it just takes whatever graph you would have had here and shifts it by that much of a wavelength, say, okay? It just shifts things right or left, and I should explain if you're observing something and you hit the button and start, a video or whatever, or start your observations at a point where this thing is not at equilibrium, like maybe where the left end of the wave is somewhat not here, it's up here, or it goes up here. At some point between here and here, that allows your initial value of y to match up with the observation. Okay, so it's kind of an initial position constant. So this implies that y of 0, 0 is a cosine of phi. So if you're observing the motion at the 0 point in space, and that is your 0 point in time, that allows you to determine phi. So phi is just the inverse cosine of whatever your initial position is over A. Now you also have to, there are two values of phi that will give you the initial position. You also have to consider whether it's at this position going up or at this position going down. Got to look at the derivative. Something you should have seen That depends what you did in differential equations. It's a pretty typical thing. And if we run into it, we'll do it, but that's pretty much what you need to know at this point. Okay? Phi allows you to adapt to whatever your initial conditions are.